All right, well, hello and welcome to this post 4th of July edition of Chem 305. I am broadcasting from a an undisclosed location somewhere up the California coast. Parthana, good to see you. I hope everybody's 4th was good. Mine was more or less. My fam and I were out of town. I don't know if you can see or notice my surroundings are different. It's because we still are. Still are out of town, and my 2-year-old had got a fever just before the 4th and has been rolling. No, he got it. What's the day? Today's the 7th. He got it on the 4th, and anyways, we're out of town. We were able to get him a doctor's appointment, which was at 1. Got him some antibiotics, and I'm here. I can't believe I'm here. Kate, it is good to see you. I have missed you all. Just starting to see the names pop up in the feed. Oh, thank you. He'll be okay. He's just, gotta kick this bug. As I'm seeing names pop up in the feed, it's like, oh, I missed you dudes. We've been hanging out a lot this summer, and 4 days is the longest we've ever been apart. So anyhow, I hope that that your holiday was good. Mine was mostly good. Taking turns pulling a sad baby. Not the funnest of times, but also not the worst of times. All right, so we are still talking about. We're still in chapter 7. Still talking about gas laws. Hey, it's Say and Susan, the S Squad. We've been having a good time. As far as having a sick little one can allow. But I'm also glad this is my first time streaming, kind of not on my own Wi-Fi network. But this one's looking good. We've got an excellent stream health, according to YouTube. So we're just going to dive right in. Now, we've been talking about gas laws. Specifically, we've been dealing with the combined gas law, which tells us that the initial pressure of a gas times the initial volume of a gas divided by its initial temperature and initial moles is equal to its final pressure times its final volume divided by its final temperature and final quantity of moles. And we did a problem last Thursday. We did an example where we got into this, and then I have another one cooked up so we can get some reps in. So let's dive into this problem-solving extravaganza. All right, so here is our first example. Oh, I guess maybe worth mentioning. This is our first lecture on the second half of the summer session. We're officially halfway through. And this is, from now on, we're getting close. Well, we've always been getting closer to the end, but we've accomplished the first half. This is the second half of the saga. All right, so let's take a look at this example. So nitrogen gas is stored. You know what? I need to reduce my screen brightness. There we go. Nitrogen gas is stored in a sealed metal canister or cylinder. At 25 degrees Celsius. The pressure The pressure gauge reads 722 torr. If the cylinder is moved to a 16 Celsius freezer, what will the pressure gauge read? All right, so here's a problem. Anytime you are trying to solve this, it's big, it's long, it's wordy, it may feel overwhelming. All right, anytime you're trying to solve it, the first thing you want to do is identify what you're trying to find. All right, that is always step number one. And when you look at this problem, what we're trying to find is right here at the end. What will the pressure gauge read? And one thing you'll notice is earlier, we're told that the pressure gauge reads 722 torr. That's an initial pressure. So here, if we're being asked what will the pressure gauge read, we're being asked to find our final pressure, right? This right here is our final pressure. All right. Once we know what we're trying to find, we need to identify what we've been given, and we've already kind of started along this path. Right, we have been given our initial pressure. P1 is 722 torr. All right, but let's look at what else we're given in this problem. We're told our temperature at the beginning of this problem is 25 degrees Celsius. So there's a T1. Oh, let's see. Oh, are we having... Okay, sorry. Yes, okay. Actually, yes to both. Parthana, we totally are. If you're wondering if we're having office hours like normal, we definitely are. And then Kate. Kate's question, which pertains to this problem, do we have to keep track of sig figs when converting from Celsius to Kelvin? The answer is totally. We totally do have to keep track of sig figs. Because remember, when you're using the combined gas law, you're never allowed to use temperature in Celsius, or Fahrenheit for that matter. You can only use Kelvin as a temperature scale. All right, so we're given T1, we're given P1, and you'll notice we're also given our final temperature, right? We're told that it's moved to a freezer that has a temperature of 16 degrees Celsius. So this is a final temperature. T2 is 16 degrees. And now you'll notice, all right, we've, okay, awesome. Okay, and while we're talking about it, we know that we can't ever use degrees Celsius, so let's just add 273 to both of these. That way they're locked and loaded and ready to go. To convert from Celsius to Kelvin, you just add 273. So T1 will be 298 Kelvin, and T2 will be 289 Kelvin. And if that just looks menacing to my dyslexic mind, So hopefully I don't confuse those over the course of this problem. One thing to notice as far as sig figs go, 25 has its last significant digit in the ones place, so does 273. So our answer must have its last significant digit in the ones place, which means that we don't need to round or add any zeros to 298 Kelvin. It's fine. Same with 16 and 273. Our answer must have its last significant digit in the ones place, and 289 does. So our sig figs are already looking good on temperature 1 and temperature 2. All right, now, it's great that we have pressure, temperature, initial pressure, initial temperature, final temperature. What about our moles? What about our volume? Because if you look at this problem, there's nothing in here that explicitly states what the number of moles are or what the volume is. But both somewhat have an answer hidden in the first sentence. You'll notice that nitrogen is stored, that first sentence, in a sealed metal cylinder. All right? If it's sealed, so there's a couple things we can glean here. Sealed means there's no gas in or out, right? If it's sealed, no gas is escaping, no gas is being added. That means that the number of moles does not change, all right? And what do you know about metal cylinders? You're like, well, I don't know much about metal cylinders. What do you know about metal? Metal's not going to change its volume. It's not going to like blow up like a rubber balloon. It's not going to deflate like a rubber balloon. Metal is rigid. So our volume does not change as well. Our initial volume is going to be equal to our final volume because this is a metal cylinder we're talking about. So anytime you have a quantity that does not change, it cancels out of this equation, all right? So volume cancels and quantity of moles cancel because both of these are constant throughout this process. So our combined gas law simplifies down to P1 over T1 is equal to P2 over T2. All right, and let's open up a new slide and solve this equation. So we have P1 over T1 equals P2 over T2. I actually need to move this piece over. There we go. And we want to solve for our final pressure, so we're going to multiply, we're going to multiply both sides by our final temperature. All right, and then we get final pressure is equal to initial pressure times final temperature over initial temperature. All right, we can plug in our values for these. Our initial pressure was 722 torr. Our final temperature was, let's see, 289. This is the one I wanted to be careful not to mix up. Our initial temperature was 298 Kelvin. All right, and our temperature units cancel, leaving us with pressure units. All right, so 722 times 289 divided by 298 gives us a value. So our answer is 700.194631. All right, sig figs wise, we can keep three significant figures, 1, 2, 3. That one will round down, but we run into a problem. We run into a problem if we just write our answer as 700, because 700 only has one significant digit and we need 3. So we're going to need to write our answer here in scientific notation. We're going to take our decimal and roll it so that it's right behind the first non-zero digit. Our final pressure will be equal to 7.00 times 10 to the second torr. And that is our correct answer with the correct units and the correct number of significant figures. All right, so that is a second example using the combined gas law. You can totally use the combined gas law to solve any of the problems that we did using the kind of smaller laws like Charles' law, etc. But that's a couple examples of how you use it to answer these bigger questions with more going on. All right, so we've been talking a lot about how pressure relates to temperature, quantity of moles, and the volume of a gas. Over the course of our discussion in Chapter 7, we've developed a lot of different... hang on. We have a question. What would you do if you had 100 degrees Celsius before converting your Kelvin measurements? So yes, Kate, technically, apply, okay. Okay, so we've developed a lot of equations relating pressure to all these different quantities that we can measure for a gas, and we've done this by saying when you multiply or divide these quantities in these given relationships, that they'll be equal to a constant number, right? That's even how we got the combined gas law. We said that the pressure of a gas times its volume divided by its temperature times its number of moles was equal to a constant number, and we said you don't have to worry about what that constant number is because we can just do initial and final quantities. Well, it's time at long last for this constant to have its day, all right? And turns out, if you're wondering, what is that constant number? What does it equal? It has a value, and this constant number is equal to R, which is the symbol for the constant number. This is called, this constant is called the ideal gas constant. That is the name of our... Just bad at drawing arrows today. There we go. R is the ideal gas constant, and if you're wondering, okay, well, but still, I want to know what it equals. R is equal to 0.0821. Now its units, the units for this constant are liter atmospheres per mole Kelvin. All right, and the reason for this is, if you look at where this comes from, you have both volume, you have both pressure and volume units in the numerator, and then you have moles and temperature units do better. Must do better. Both temperature and moles in the denominator, so that's why the ideal gas constant has the units that it does, because you got pressure and volume in the numerator, moles and temperature in the denominator. All right, this is the ideal gas constant, and it allows us to kind of get away from having to use initial and final quantities of gases. We can just, now that we know what the constant is, use the pressure, temperature, volume, etc., and moles all interconnected without having to have them in double. All right. Now we can also do a little bit of algebra on this equation, right? For starters, we're going to get rid of the denominator because no one likes the denominator. Let's multiply everything by nt. It'll cancel on this side, and we get a rearranged equation. As PV is equal to nRT. All right, and this is known as the ideal gas law. Oops. The ideal gas law, and it is awesome. The ideal gas law is awesome for one reason and one reason alone. You can find that reason here. What does N stand for? Well, N is the symbol that stands for moles. All right? And what do we do with moles? Well, we only do one thing with moles, and that is stoichiometry. All right, what is stoichiometry? Well, that's balancing chemical equations, that's percent yields, that's limiting reactants, that's all that stuff we learned to do in chapter 6. This equation allows us to relate pressure, volume, and temperature, these quantities that can be measured for a gas, relate them all to moles, and that allows us to do all the cool stuff we learned in chapter 6 now with the equations we're learning in chapter 7. It's so ideal gas law gives us moles, which leads to stoichiometry, which leads to, I don't know. This is for you to decide. But one way or another, whether it's true love or something else, this is where we're going. So let's cook up a couple of examples. And put the ideal gas law into the context that you'll be running into it, encountering it on, almost at exam 2. This is not an exam 2, it'll be on the 3rd exam. Okay, so let's look at an example. Solid calcium carbonate decomposes at 453 degrees Celsius and 1.02 atmospheres of pressure into solid calcium carbonate. That was a reactant. It decomposes into solid calcium oxide and carbon dioxide gas. All right. Part A. let's balance this chemical equation. Part B. Part B. If 1.00 grams of calcium carbonate decomposes completely, what volume of carbon dioxide is produced? All right. Okay. Here is the problem in its entirety. So let's hit up part A. Let's balance this chemical equation. And to do that, you'll notice we have to kind of do some nomenclature. So we have here calcium carbonate. Calcium, we can determine its charge from the periodic table. It has a charge of +2. Carbonate has a charge of CO3 with a oh my gosh, it doesn't have a charge of CO3. It has a charge of -2. It has a formula CO3. It's one of our polyatomic ions. All right, so because the charges here are equal, calcium carbonate combines in a calcium and carbonate combine in a 1-to-1 ratio. All right. Now this is going to produce calcium oxide, right? Solid calcium oxide. We already know the charge on calcium oxide. When you look at the periodic table, you realize that it has a charge of -2. So it will combine in a 1-to-1 ratio with calcium as well. So this makes CaO in the solid state. Then we add our last component, carbon dioxide gas. That's a covalent compound. It has 1 carbon, 2 oxygen. And it is in the gas phase, which is critical for us using the ideal gas law. So we've written out our reactants, we've written out our products. Now let's balance this chemical equation after we get rid of these weird colored lines and these ions for that matter. All right, so when we go to balance this chemical equation, we take our inventory. We have calcium, carbon, and oxygen on both sides of this chemical equation, and we have 1 calcium, 1 carbon, 3 oxygen on our reactant side. On our product side, we have 1 calcium, 1 carbon, and then 1 + 2 oxygen. And you'll notice that each element present is already balanced. Now, if you're going, okay, how realistic is that? Like I, as a student, always hated when professors would do the thing where they give themselves the easiest example to work in class, and then you're like, yeah, but the test is going to be harder, so you're just, drinking my chain. I have literally put this exact problem on exams, even after doing it in class, and students will can't accept that I gave them an equation that was already balanced, so they do something awful, like they'll add a 2 somewhere, right? Don't be that guy. If I give you something that's already balanced, just say thank you and move on. Don't try to fix what isn't broken. All right, so this is our balanced chemical equation. Now let's get to, so that's part A. let's get to part B. All right, part B. We're told, sorry, let me pull up my notes, that this reaction, that this reaction takes place at 453 degrees Celsius and 1.02 atmospheres of pressure. We're told that we have 1.00 grams of calcium carbonate, and we're asked to find the volume of carbon dioxide, all right? And instantly, what should grab you is you're being asked to find the volume of a gas. So that should make you immediately think of the ideal gas law, all right? Now, when you look at things, we have a temperature, which goes here. We have a pressure, which is right here in the equation. And you will always, always, always have R. All right, R is a constant. It's the same in every problem. It's 821. So that means the only thing we need to solve this problem is we need our moles. All right, we need our moles. And we weren't given moles. What we were given are grams of reactant. Now, you can take your balanced chemical equation, go from grams of calcium carbonate to moles, and then use the fact that you know there's a 1-to-1 molar ratio from moles of calcium carbonate to decomposing to moles of CO2 produced. You can use that relationship to determine your moles of CO2, all right? So we've been given all the other pieces, but we need to use stoichiometry to find that last puzzle piece to solve for our volume. All right, so let's start doing our stoichiometric heavy lifting. We have 1 gram of calcium carbonate. Excuse me for leaning over. I'm just gonna grab, there it is. The old-fashioned periodic table. Normally I have, at home in my office, I've got like this sweet setup with a couple monitor screens, but I'm going mobile, so my setup is a little more restricted. So I'm using the old-fashioned, the pen and ink printed word. Okay, so we need, the reason why I pulled out the textbook is we need to convert from grams of calcium carbonate to moles, and to do that, we need to calculate a molecular weight. Now, calcium has a molecular weight of 40.08-ish. Let's see. Yep, there we go, 40.08. Carbon, 12.01. Oxygen is 16, but we've got 3 of them, so it'll be 48.00. And adding these all together comes out to 100.09. I'm just going to double check with my calculator because it seems like a weird number, and so. Yep, my mental math was correct. So 100.09 is my molecular weight of calcium. Grams of calcium carbonate cancel. Next, we convert from moles of calcium carbonate to moles of CO2. And we have, from our balanced chemical equation, we know that it is a 1-to-1 molar ratio. So those two cancel. And you'll notice we can stop here. Because we're not trying to find grams of carbon dioxide, we need moles to plug it into this equation. So we're good to crunch our numbers. We have 1 divided by 100.09 times 1 divided by 1. Comes out to be, we can have 3 sig figs, 0.009, oh wow, 999 moles of CO2. All right, now that we know our moles, we can solve for volume, right? Pressure times volume is equal to moles times R times temperature. You can divide both sides by pressure to isolate volume on one side of this equation. So volume is equal to the number of moles times R times T over pressure. All right, and our molar quantity is 0.00999 moles. Oh, let's see. I'm going to run out of space here. So I'm just going to move this down here. 0.00999 moles. Now, R is 0.0821, and that's liter atmospheres per mole Kelvin. And here with the ideal gas constant, you can see that we need all of our quantities to be in liters, atmospheres, moles, and Kelvin, because if they're not, then the units won't cancel. Fortunately, our pressure is in atmospheres, but you'll notice that our temperature is in Celsius. So if we're going to do this unit conversion real quick, we got to add 273. So it'll be 6. 5 plus 7 is 12. So 726 Kelvin is the temperature we need to plug in. And when we do, you'll notice that Kelvin cancels Kelvin, atmospheres cancel atmospheres, and moles cancel moles, leaving us with a volume unit, which is good because we're solving for a volume. All right, now let's crunch our numbers. 0.00999 times 0.0821 times 726 divided by 1.02 gives us a volume of 0.584 liters. All right, and that is our volume of carbon dioxide produced when 1 gram of calcium carbonate decomposes. Just when you thought you had seen it all, and you put stoichiometry in your rear view, it finds a new and excited way to reinsert itself into the conversation. It's like the ex that you had that can't stop showing up to the same parties and hangs that you're at and trying to talk to you with your new relationship, gas laws, and here comes stoichiometry saying, hey, let's all hang out, and it's awkward and uncomfortable for everyone. But I do need to just tell you, stoichiometry is a toxic X. It's going to keep doing this. And all we can do is just try to shut it down as best as we can. But we can't control it, sadly. All right, that's one example. Let's do another. All right, let's look at, oh, this is interesting. Oh my gosh. Okay, so next example. Let's look at this. So even I wrote X on this page. It's so appropriate. I'm just gonna, yeah, okay. Aqueous. Oh, wait, no. Yes, okay, I'm fine. Aqueous HCl reacts with solid sodium hydride at 25 degrees C and 0.97 atmospheres. To produce hydrogen gas and aqueous aqueous sodium chloride. All right. Part A, write a balanced chemical equation. Part B, Part B reads like this. If, oh, did not mean for that to be in blue. If 4.80 liters of hydrogen gas was produced, how many grams of sodium hydride reacted? All right. So, step number one, we need to write, whoa, I did not mean to blank that out, sorry. We need to write a balanced chemical equation, and we're given a reaction between aqueous HCl and solid sodium hydride. All right. Sodium, when you look at the periodic table, it wants to be like its nearest noble gas, so it's going to lose one electron. Hydride is hydrogen as an ion. Now, hydrogen's nearest noble gas is helium, so it wants to gain an electron. So we have a positive one and a negative one. These two are going to combine in a 1-to-1 ratio. All right, and this is a solid, and these two produce hydrogen gas. Now, hydrogen is a homonuclear diatomic, right? It's H2. And then we're dealing with aqueous sodium chloride. Now we have sodium, chloride is -1, so again, we're dealing with a 1-to-1 ratio here. NaCl in the aqueous phase. All right, that is our balanced chemical, or this is our chemical, these are our reactants in our products. Now we need to balance our chemical equation. So let's take a look. So we have hydrogen, chlorine, and sodium. All right. On our reactant side, we have one hydrogen from HCl and one hydrogen from sodium hydride, and one chlorine, one sodium each. On our reactant side, we have two H's and H2, one chlorine, one sodium. Again, pre-balanced. If you get one of these, accept it. It's a gift. Enjoy it, and let's roll with it. Right? Stoichiometry is hard enough as it is. You don't need to try to complicate things. Take a pre-balanced chemical equation. Now, we've been told that this reaction proceeds at 25 degrees Celsius and 0.97 atmospheres. We're also told that it produces 4.80 liters of hydrogen gas, and we're asked to find the grams, the mass of sodium hydride. Now, you'll notice we're given a bunch of information about this gas, right? We're given the temperature. We are given the pressure. And we are given the volume. All right? We always know what R is because R is a constant number. It never changes. So we have all the information we need to find moles of hydrogen. Now, how can that help us? Well, we need to find grams of sodium hydride. So if we knew the moles of hydrogen, we could use the 1-to-1 molar ratio in this balanced chemical equation to convert from moles of H2 to moles of sodium hydride and then to grams. So our tactic here is to use the ideal gas law to find moles of hydrogen and then use our balanced chemical equation, some stoichiometry magic, to go from moles of H2 to grams of sodium hydride. All right? So we want to enlist the use of the ideal gas law, PV equals nRT. Sorry for those scribbles, there's a little something on my screen. We want to isolate moles on one side of this equation, so we'll divide both sides by RT. They cancel, and we get moles are equal to pressure times volume over the ideal gas constant times temperature. Now, before we can plug these numbers in, we do need to convert from degrees Celsius to Kelvin. Oops. So we add 273 to convert our temperature to the appropriate temperature unit. Now we can plug everything in. 0.97 atmospheres times a volume of 4.80 liters divided by 0.0821 liter atmospheres over mole Kelvin times our temperature in Kelvin, which is 298. And you'll notice temperature units cancel. Jen, great question. Jen asks, will we most likely always be looking for moles? And Jen, that is a great question. What I will say is, though moles may not always be the answer you're looking for, they kinda always will be how you find the answer. Yes. So you can expect moles to rear their ugly head like the X you don't want to run into. They will find you, and you will have to deal with them in social circumstances, at least until this semester ends, or summer session ends. Volume leaders cancel volume, leaving us with moles. So let's crunch our numbers. We have 0.97 times 4.8 divided by 0.0821 divided by 298. This gives us a, let's see, we can keep two sig figs here. So 0.19 moles of H2. That's how many moles were produced. And now, we can convert our moles of H2 to moles of sodium hydride because we have a balanced chemical equation telling us that they have a 1-to-1 mole ratio, that every 1 mole of H2 produced came from 1 mole of sodium hydride that reacted. Now we can convert from moles of sodium hydride to moles, sorry, not moles, to grams of sodium hydride. We need to calculate a molecular weight. Sodium has an atomic mass of 22.99. Hydrogen has an atomic mass of 1.01. When you add these two together, my calculator is telling me the answer is 24, but I need my last significant digit to be in the second decimal place, so the actual atomic mass is 24.00 grams in 1 mole. Moles of sodium hydride cancel, and now we crunch our numbers. 0.19 times 24.00 comes out to be 4.56, but we can only keep 2 sig figs, so that means our final answer will be 4.6 grams of sodium hydride 4.6 grams of sodium hydride reacted to produce 4.80 liters of hydrogen under these circumstances. All right. Okay. I'm looking at the next problem, and I'm looking at the amount of time it's going to take to do it, and I think it's going to take more time than what we have to give to it. So we're going to go ahead and pause here. You know what I will do, though? So we're not going to work this problem today. We will do it tomorrow. Let me set up the problem now. You can take a crack at this tonight. We'll do it tomorrow, and hopefully you'll gain something from the process. So let's take a look at this example. Oops. nitrogen trihydride gas. Oops. Decomposes into nitrogen gas and hydrogen gas at 212 degrees Celsius under 0.73 atmospheres of pressure in a 15.0 liter metal cylinder. All right. Part A. Write a balanced chemical equation for this reaction. Part B. And here's the tricky part. Part B. If all the nitrogen trihydride completely decomposes. If all the nitrogen trihydride completely decomposes, what is the total pressure in the cylinder? All right, and I'm going to give you a hint. Here's the hint. Remember, two gases are produced in this reaction. All right, that means you have two pressures. Add up. ... All right. There's a cliffhanger. This is for you to take a crack at on your own. See if you can do it. Come back tomorrow at 1:20 and we will walk through this one together. Cool? Okay. If there are any questions, I can totally take them. We still have a little bit of time left in the lecture. If not, we'll go ahead and pause here, and we'll be back at 3 for office hours. Office hour 1 for week 5. Alrighty. Okay, I'm going to go ahead and put a pin here in lecture. I'll see you all in about 30 minutes. Later.